Hello everyone, my name is Marco Heisig. Welcome to my talk about sealable meta-objects for Common Lisp. The main goal of my work is to speed up certain calls to generic functions. As a motivation, I want to show how my libraries can be used to implement a very fast version of the two-argument plus function. To do so, we define a generic function 2arg+ just in the usual way, except that its function class is fastGeneric function. Afterwards, we can add methods in the usual way, for example for arguments of type float, number, or string. For the particular method specialized on arguments of type float, we also show that it is possible with fastGeneric functions to add method properties. Particularly here we use the inlineable method property, and once all these methods have been defined, it's possible to call the function sealDomain for this function and the domain of numbers. And once these definitions are all in place, the following compiler optimizations will happen. For each call to this 2arg+ function, if the compiler can determine that all the arguments are of type float, then the function call will be replaced by an inline effective method and typically boils down to a single assembler instruction in this case. Even if the arguments are just of type number and not necessarily of type float, the compiler can still optimize and typically bypass the discriminating function and directly call the correct effective method. But the most important property of fastGeneric functions is that outside of the sealed domain, they behave just like regular generic functions with the same performance characteristics, but also with the same extensibility, so it is possible outside of the domain of numbers to add further methods. I want to talk briefly about the project history. Everything started in 2018 when Robert Strand wrote on the SICL IRC. I figured out a few things that interested people could help me with if they want to, like Astella or Heisig. One thing would be to finish the implementation of the sequence functions. Well, I volunteered. And after working on this for a few months, I had this idea to implement sequence functions via suitably restricted generic functions. This is where the yuck shave begins, because in order to implement those suitably restricted generic functions, I need a formalized way how to see the behavior of meta-objects. And there I go, and I had to implement not one, but two additional libraries that are now on QuickLisp. And as of today, I have those two QuickLisp libraries, but unfortunately the sequence functions are not finished. Introduction. Before I want to explain the machinery, I want to talk a bit about the background and explain the most important concepts. Everything in this talk is essentially based upon this book, The AMOP, The Art of the Meta-Object Protocol, which, according to Alan Kay, is one of the best books written in computer science in a decade or so. It was published in 1991 and describes the de facto standard for the Common Lisp object system. De facto meaning not everything from the AMOP is in the Common Lisp specification, but there is a portability library called AMOP that provides everything that's specified in this book in Common Lisp and on any implementation. So in order to get started, I strongly recommend to you to use AMOP. There is another additional resource that I very much recommend. There is an HTML reference for every definition in the AMOP. All the generic functions and classes involved. It's on metamodular.com/clausmop. Some of you in the audience may ask now, what exactly are meta-objects anyway? And this is a specialty of Common Lisp. In Common Lisp, every object has a class. And furthermore, every class is itself an object, meaning we get a potentially infinite tower of classes on top of classes. And I try to illustrate this here for some examples. So typically a programmer works with something like a number or a string or a function, or an instance of some class. But Common Lisp also allows us to take those classes as first-class objects, so we end up with the class integer, the class string, the class function, or our class foo that we defined ourselves. And we can go even further. We can ask what is the class of the class integer and end up with the class built-in class, or we can ask what is the class of the user-defined class foo, ending up with standard class. And we can go further and further up the hierarchy, and this only ever terminates because the standard class is an instance of itself. And all the classes in the blue box that I've shown on the slide, those are class meta-objects. Meta meaning they are above the layer what we usually consider as objects. In addition to class meta-objects, the AMOP also defines generic function, method, slot definition, method combination, and EQL specializer meta-objects. The other ingredient we need to understand this talk is what exactly happens when we call a generic function. And the most important 4 steps are shown here. Whenever we call a generic function, we actually call the discriminating function of this generic function. And the discriminating function then uses the identity and the classes of its required arguments to compute a list of applicable methods to these arguments. These applicable methods are then sorted in order of precedence or in some other way, and then a method combination is applied to them to determine an effective method. And this effective method is then finally invoked with those arguments. And the only reason why this is not prohibitively slow is that the steps 2 and 3 are typically cached. And this cache is cleared whenever a meta object that is involved in this protocol is modified. That can be the specializers of a method, the method, or the generic function itself. We want to perform the steps 2 or 3 statically, and we want to replace step 1 with step 4 when appropriate. So we don't want to do this invoke this machinery at runtime at all. Whenever possible, we want to do it at compile time. And we can only do so safely if all involved meta objects are sealed in some way. Which brings us to the first section of the talk. Meta-object sealing. So my first task was to come up with an exhaustive list of the things we have to forbid in order to perform any compile time optimization on arbitrary meta-objects, and I ended up with this long list of properties that I will just read out. A sealable meta-object has 2 states, either sealed or unsealed, and once a sealable meta-object is sealed, it remains sealed indefinitely. Calling reinitialize instance on a sealed meta-object has no effect. It is an error to change the class of a sealed meta-object, and it is an error to change the class of any object to a sealed meta-object. Furthermore, it is an error to change the class of an instance of a sealed meta-object, and each superclass of a sealed meta-object must be a sealed meta-object itself. Good thing about these properties is system classes and structure classes in Common Lisp automatically fulfill these criteria, and our implementation will treat them as such. This is also the reason why we could just specialize on floats or numbers in the motivation example. Another concept we need to introduce is that of domains. A domain is the Cartesian product of the types denoted by some specializers. A sealed domain is a domain whose constituting specializers are sealed. That means either they are a class that is sealed or an EQL specializer whose object is an instance of a sealed class. And often we talk about the domain of a method. The domain of a method with n required arguments is the n-ary Cartesian product of the types denoted by the method's specializers. And for convenience, We also introduced the concept of domain designators, so lists of type specifiers that can be turned into specializers or specializers themselves. Now that we have introduced the concept of sealable meta-objects and domains, we can finally define sealable or sealed generic functions. A sealed generic function can have any number of sealed domains attached to it, subject to a few constraints. New sealed domains can be added by calling a sealed domain, as we've already shown. But all sealed domains of a generic function must be disjoint. Furthermore, each method of a generic function must either be fully inside a sealed domain or fully outside. And each method inside of a sealed domain must be sealed and all its specializers must be sealed. It is an error to add or remove methods inside of a sealed domain, and it is an error to create a subclass of a sealed class that would violate any of the previous rules for any sealed generic function. The last rule might seem a bit odd, but the alternative would be to disallow multiple inheritance with sealable meta-objects involved. And all these rules could be boiled down to: within a sealed domain, once the generic function, the domain, and the methods have been sealed, nothing will change anymore. And there is one final concept that I want to mention. It's called automatic sealing. You have heard about sealed meta-objects and sealable meta-objects, and some of you may have worried, do I have to figure out what do I have to seal in the right order? And the answer is no. We have automatic sealing. Whenever a sealable meta-object is sealed, all its superclasses are sealed automatically, or an error is signaled. When a sealable method is sealed, all its specializers are sealed automatically. And the function seal domain automatically seals the supplied generic function and all methods inside of the designated domain. As a result, the distinction between sealed and unsealed meta-objects is mostly irrelevant to the user and everything just works. And now finally we have the prerequisites for what we actually wanted to do, which is to implement fast generic functions. I don't want to discuss every step in detail, but rather highlight the three most challenging tasks when writing these optimized fast generic functions. Challenge number one is telling the compiler if and how to optimize a call to a sealed generic function. Challenge number two is computing the set of methods applicable to those types at compile time or at load time. And challenge number three is computing either an inlineable effective method or a directly callable effective method function. And the bonus challenge is, I like portable code, so can I do this with 100% portable code? Except that I use close AMOP. And the answer is yes, with some trickery. So what I show here is a function that generates a compiler macro function for a supplied fast generic function FGF. How it works is, when it is invoked, it traverses all the sealed domains of the fast generic function. And then for this domain, it traverses what I call static call signatures, so all the islands in the domain that have a fixed list of applicable methods. And then for each static call signature, we check that all the argument forms are of the types that are required by the static call signature, and if this is the case, we return an optimized function call. The magic part here is the function compiler type p that I came up with. Compiler type p takes three arguments: a form, a type specifier, and an environment, and it returns whether the result of evaluating this form is of the specified type. The trick is a use or abuse of the function constant p. So we call constant p in this environment of a form that is a constant if and only if the form is of this type, and otherwise it diverges to, the diverging part is this tag body label go label, just an endless loop. So either it terminates and returns nil, or it loops forever. And a sufficiently smart implementation of constant p will then look into the environment and figure out the correct knowledge for us. And there is also a fallback clause. Even if this constant p function doesn't do anything useful, we can still check whether the form itself is constant p, call eval on it, and check whether this result is type p of this type in the environment. If you think this looks too good to be true, you are unfortunately right. There are several flaws with this portable implementation. One being it's of course slow. I've shown 3 nested loops over a constant p, type p, and eval. But the bigger problem is in practice it only works reliably for literal constants. Most Lisp implementations don't have a very smart implementation of constant p. And the other thing that bothers me is this version depends on compiler macros, and a compiler is allowed to ignore all its compiler macros. So this is not a reliable way to achieve what I want. So instead, in practice, we use whatever mechanism an implementation provides, for example, def transform on SBCL. Challenge number 2, computing applicable methods. We use the only sane way of computing all applicable methods, which is by calling compute applicable methods. The actual challenge is that compute applicable methods doesn't accept types or specializers, but arguments. Our solution is that we introduce static call signatures, and a static call signature consists of a domain, a list of types, and a list of prototypes, each of the same length. The types denote a subset of the domain with a fixed set of applicable methods, and each prototype is of its corresponding type. The prototypes are chosen such that they unambiguously identify that particular subset of the domain. And the real challenge is thus choosing suitable prototypes. For example, if we have a domain and methods therein, one specialized to the class of integers and one specialized with an EQL specializer of 5, we must not fall into the trap and accidentally use 5 as a prototype for the former, because it would also designate the latter. So we have to make sure that those prototypes actually describe the precise set of methods. And the final challenge that we had to solve is computing the effective method. And there's some good news here. The good news are there is a function called compute effective method. The bad news is the result is not something we can call, but rather a form containing some very arcane magic macros. There is one possible solution, and it's also 100% portable, by the way. I've sketched it here. In reality, you would do it a bit more sophisticated, but the rough idea is you just define an around method on the arguments, and if a special variable is set, we return the function call next method for further use. Otherwise, we call the next method. And then to obtain the effective method function, we can just set the flag, call this function with the right arguments, and then use the next method that gets returned. The trouble here is this is not exactly something typical where most class implementations optimize for. So if you start writing code like this, you lose an order of magnitude in performance, and you shouldn't call this a fast generic function. So in practice, we have to do something completely different, which is we expand the effective method ourselves using our own versions of call method and make method. And therein we define local functions for call next method p, and so forth. But with all this in place, we can finally apply some optimizations. And the three most important optimizations are, firstly, inlining of effective methods. Then, secondly, calling the effective method directly and skipping the discriminating function when possible. And the last optimization that's quite rewarding in practice is inlining of keyword parsing only. So whenever we have a generic function with keywords, and we are within a sealed domain, we can statically determine all the keywords within this sealed domain and generate a keyword parsing function that internally calls an effective method that doesn't use keywords. And if we inline the keyword parsing, a compiler can usually optimize it away entirely, and this gives quite the speed up. With all this in place, it's finally time for some examples and benchmarks. At first I wanted to show a toy example, but why not go for the full thing? So here I show an excerpt of the source code of SICL Sequence. If you are interested in SICL Sequence, the entire source code is on GitHub with the URL I've shown below here. And the definition of sequence function is now quite pleasant. We say a sequence function is a fast generic function with the appropriate meta class because we intend to call it. And then we can say the function alt is just a sequence function, the function length is a sequence function, and the function find is a sequence function. On the next slide, I show the exciting part, which is how can we define further methods on such a sequence function. In particular, I show the definition of all the methods specialized on vectors, because this also illustrates an important concept that many people have asked me, which is it possible to specialize on certain subclasses of vector, like a vector of single floats and double floats, and is it possible to do this portably? And the answer is yes and yes. So here I use a macro called replicate for each relevant vectoroid that takes the body and replicates it for every single subclass of vector, including vector itself, and substituting one of the symbols, in this case this uninterned symbol vectoroid, with the relevant class. So on some implementations we might end up with only 3 versions of find specialized to vector, simple vector, and bit vector. But for example on SBCL we end up with 35 specialized methods, and within each method we get the full optimization because we know the size of the words that are being processed and so on. I won't go into detail about the method body because this is already described in the paper Fast, Maintainable and Portable Sequence Functions by Durand and Robert Strand. And once all these methods have been defined, all we have to do is call seal domain on the domain of t and vector to get all the compiler optimizations. And now comes the point where I have to look at the benchmarks and say, was it worth it? And the answer is luckily yes. So what I show here in this benchmark table is the timings in nanoseconds for finding things in certain sequences. The first column is the compiler knowledge about the element type. The second column is how many keywords we supplied to the function. And then the first group of 3, labeled one element, shows the timings for processing sequences of length 1. And the second group, labeled 50 elements, lists the timings for processing 50 elements. And first I want to look at the one element group, because this is actually the most interesting part, because we don't care about the speed of processing the sequence itself, we care about the cost of dispatch. And we first look at the case where we don't have any knowledge about the element type. And it's not surprising then that the regular SICL implementation and the SICL implementation with inlining turned on in the next column is exactly equally fast, because inlining doesn't work if we don't have any compile time knowledge. But the good news is, without keyword arguments, we are exactly as fast, or almost exactly as fast, as the SBCL version, and we get some slowdown with keyword arguments added, but only in the case where we don't have any element type knowledge, and this is just the regular generic function invocation overhead. And also if we look then in the 50 element column, we see that this overhead is not so significant anymore for larger vectors. The really interesting part is, the case where we have compile time knowledge and all our machinery is invoked. And here we see that SICL Sequence is in this case much faster than what SBCL does, or at least a few nanoseconds faster, depending on whether we use inlining or not. And the lowest 4 rows also show the timings for processing lists. The only thing I can say here is there seems to be a very small inefficiency the way we process lists and the way SBCL processes lists, but I intend to fix this in the future. The take-home message is the one slide implementation that I've shown. I will go back to it now. So this definition of find for all sorts of vectors is roughly exactly as fast as what SBCL does, the difference being that in our case the definition fits on a single slide, while in SBCL this is several pages of sequence-specific code. So this is quite motivating. It's time for the conclusion slide. We've presented 2 libraries. The library Sealable Metaobjects can be used as a foundation for any project that attempts static reasoning about objects or meta-objects. And the library Fast Generic Functions is a drop-in replacement for any generic function that is used in performance-critical code. Fast generic functions almost always outperform handcrafted solutions, and if you have a handcrafted solution that is still faster, write me and I try to fix it and get the same performance, because I really want to relieve people from hand wiring their keyword parsing code. And the most important part, feedback and experience reports are most welcome. Thank you everyone for listening. If you have questions or suggestions, you can reach me over a variety of channels. Thanks again.